Alright, so people, here's the situation. We have this chain of resistors here with these triangle patterns going back and forth. And what we are meant to do is first get an analytical form for the system of equations which describes the voltage values at each of the junctions labeled here, but also write a code which solves it so that we can know what the voltages are at each point. So that first part of the problem is a proof. We have to prove that these are the system of equations that we're working with. And it's because all of the resistors have the same value R that they don't show up in any of these equations because all the resistance values are the same. And the way to get those equations is for each junction, you take the voltage at that junction. This is the V1, so this is V1 up here, and you subtract off the voltage that is attached to it via a resistor, divide that by the resistance value, but then do that for every other voltage junction which is connected to that junction via a resistor. You do it for every single one. And so you do that for the V1 junction, you do that for the V2 junction and the VI junction, as well as the Vn minus 1 and the Vn junction to get 5 different equations, which are these 5 different equations. So if you wanted to put that problem in matrix form, it would actually look like this, where you have the top left element of the matrix is 3, and so is the bottom right. And then the second row down is this kind of strange minus 1, 4, minus 1, minus 1. But then every row in between those is minus 1, minus 1, 4, minus 1, minus 1, 0, and then zeros on either side, right? This is going to be the vector that you use for solve for for the voltage for each one. And on the right-hand side, you see it's equal to the column vector V plus, and then a bunch of zeros because, again, the first equation and the second equation have V plus on the right-hand side when you solve it. Then all the other ones in the middle are 0, so it looks like that. We need to make a code that solves this for general n. This is just a function that we got from the online resources called banded.py, which defines this function called banded, which takes a banded matrix and solves it for the solutions to the vector. But also, we can go ahead and run this, but we need to also set up the code to be able to use it. So let's start here. So import numpy as np. We need the n of the array, so it's a square matrix, n by n. The problem assigns the number 6. We also need V plus. The problem assigns the number 5 volts. And we can set up the array, which I'm just going to call A, as a n by n matrix with float values. And actually, I want it to start out as zeros, a zeros array. And we're just going to change the values as we go. All of the first row and the last row, I'm actually going to hard code in. And then the ones in between, actually, you know what, it might be worth it to hard code the first row, the second to last row, and the last row. Let's go ahead and just do that. So A 0, comma 0 is equal to 3, so the first diagonal element. And then this guy is also true for n minus 1, comma n minus 1, because when you make an n by n matrix, you have to index the last element as n minus 1, n minus 1. That's Python for you. Then we can do the rest of the first row. So 0, comma 1 is going to be minus 1, and so is 0, comma 2. but then the rest of the first row is zeros, so that's nice. Similarly, we can do the rest of the last row. That's going to be A indexed n minus 1 comma n minus 2 equals minus 1, and also the column before that, so column n minus 3 has that value n of minus 1. The second row, a1 comma 0, this is going to end up being minus 1. a1 comma 1 ends up being 4, actually. 4 here, right? And then after that, there's another minus 1, and then another minus 1. So let me copy this and make this a 3, right? So that's the second row, then the second to last row. So this is a indexed n minus 2, comma n minus 1. That ends up being minus 1 again. And then the diagonal element on the second to last row, so n minus 2, comma n minus 2, ends up being 4. And then the two columns that precede that also end up being minus 1. So this is going to be minus n minus 3 equals minus 1. And then also the next element to the left. So n minus 4. Yeah, that ends up being minus 1. But okay. The rest of the elements of the matrix we can just put in via a loop. So let's go ahead and make a for loop I in range n minus 2. And actually want to start with row 2, go to n minus 2, right? And we just put in the diagonal element, so I comma I, that's always 4. And then the there's minus 1s on either side of that. So I plus 1 is minus 1, and then also copy this down again. Plus 2 ends up being minus 1, and also a indexed I comma I minus 1 equals minus 1. Let's move that outside of the indexing. Equals minus 1, and then the element to the left of that is also minus 1, so I minus 2. Okay. With all that done, let's check that it actually does the matrix correctly. And it does, so we're cool there. Yeah, those are all, that's how that's supposed to work. We can arbitrarily expand that to any dimensions, of course, so n by n. So this goes to like, this is a 10-sided 10 element by 10 element matrix. Oof, I can't hardly speak. I should make YouTube videos when I can't speak. But okay, that's a lot of hard-coded values and also some soft-coded in values for the matrix. We can just straight up solve it with numpy.linearalgebra.solve if we wanted to. So we can set up the input matrix or input vector and p.zeros. It's just going to have size n, float int values, and then the first one of that v there ends up being v plus, and also the second one is v plus, but the rest are zeros. So okay, that can be v plus, and also v1 equals v plus, and we can use x equals numpy linealgebra dot solve with the arguments a comma v, and print x. We can see what the values of the voltages are, right? Epic. The next part of the problem is a little bit stranger because we want it to be able to work with n equals something very, very large, right? So 10,000. But if you just try and plug in 10,000 into the linear algebra solve function, it's not going to like it. It's not going to have a great time. I don't even think it's going to finish running. It's just going to take a while. Stop. Yeah. I had to restart the runtime to stop that from going too much. So what we can do instead of doing that method is we can solve it by turning it into a banded matrix and running it through this banded matrix code, which greatly reduces the computation time, and I know it works. But turning it into a banded matrix is something that's a really interesting process. So we're going to, first of all, this function, def banded, takes as argument a banded matrix, the input vector, which we already have, and then up and down. What are up and down, you might ask? Well, up and down are just how many values are above or below the matrix that you're defining, the diagonal elements of the matrix you're defining. So if you look at this matrix again, let me just print A this time. You can see that this is the diagonal, right? 3, 4, 4, 4, 4, 3. Above the diagonal elements in the middle, there's 2 elements above it and also 2 elements below it. So that means the up equals 2 and also down equals 2. So let's hard code those in. Up equals 2, down equals 2. We'll have those values for later. To turn it into a banded matrix, you basically want it of the form where it's not n by n square matrix anymore, but a matrix that is n columns long, but then only 5 columns like wide, because you only want the non-zero values basically. So we're going to create a banded matrix. Then we're just going to call it A, B. And it's going to start out as zeros. And it's going to have the size 5, or it's going to be n by 5. That's not right. It's 5 rows and columns. And let me actually put those in here. And then also, let's, instead of making it hard 5, make it general and just make it 1 plus up plus down, because that's the same thing. And it's going to be floats matrix, right? Then for I in range n and for j in range n as well, we can go in here and define what the values of the banded matrix are. And also the range here is actually not what we want, because it's going to turn out that you don't want to put in new values of 0 as you go down. So let's instead make the lower bound of this the maximum of a list, which includes 0 and I minus down. That way we can ignore 0 elements in the Aij matrix and we're not taking forever to run this. Also, let's make the maximum value for the range the minimum of the list, which includes n and I plus up plus 1. And it's not uppercase I, it's lowercase I. Again, to avoid appending more zeros into it. But then you take your banded matrix, specifically the element up plus I minus j, comma j, and you set that equal to a indexed I comma j. We can print out what the banded matrix is going to look like. It's this second matrix down here. Now you can see it's not an n by n square matrix like this guy. Instead, it's a it's a 5 by n matrix where you just have a lot less zeros, and the values in the middle are the ones that really contribute to the function. Okay, so now you can run that through the Mark Newman's banded.py code. and just all it's going to do is going to do a function call, banded, and then you run through it A, B, V, and up and down, and you can print out what the result of that is. Let's also print out the the old solution that just uses linear algebra.solve, just to verify that they are the same, and they are. I mean, look at those numbers; they're all identical. So we know that the thing works. Now we can turn it up to 11 and solve for the system of 10,000 resistors instead. And it gets done in like less than a second. So it uses the banded form of the matrix to do that calculation. You saw that it was very fast, and it gets a bunch of values that are between 0 and 5, which is what you expect for a series of resistors like this. All right.